Hello, here's the question number 26, which says a coil is made by winding a large number of turns of a thin wire on a hollow plastic cylinder. A magnet is inserted in the coil and its ends are short circuited. The magnet is suddenly removed immediately after removal of the magnet. If in first two consecutive time intervals of 0.1 second each amounts heat dissipated in the coil are delta W1 and delta W2 with these numbers respectively, find total amount of heat dissipated in the coil. So this is basically large number of turns wounded in a hollow plastic cylinder. So that's kind of solenoid, and this bar magnet, when it was inside, it had created the magnetic flux passing through it, and once it was suddenly removed, then you will find there will be flux change. That flux change will have immediate some current, and because of that current, then after this current will decay to zero, and therefore it will generate heat because the coil has a resistance. So the effective circuit we can think of is this inductor of this circuit and resistance in the circuit, and this short circuited. Let's say at any time the current is I, and which started with I naught as initial current, which was a constant number. So we know this is LR, decay of current case, which is the standard case, and we have already solved that case to find out the current in this circuit as a function of time, which turn out to be I is equal to I naught e raised to power minus RT by L. So this is how the current is going to decay in this circuit. Now the question is demanding how much the heat will be dissipated. So heat will be dissipated via this resistance, or we can say that will be a decrease in the stored energy of this inductor. So heat dissipated in the coil in time t can be written as this W is equal to minus delta U. That means decrease in the potential energy stored in the inductor, which will be basically initial potential energy minus final. Initial can be written as half L I naught square because initial current was I naught, minus half L I square, where I is the instantaneous current. Now from here we can take this half L outside, so it's like I naught square minus I square, where I is this number which we can put over here. From here we can take this I naught outside, so it becomes work done is equal to, or basically heat. This W is indicating heat dissipated. So heat dissipated is equal to half L I naught square within bracket 1 minus e raised to power minus 2 RT by L. Now this L I naught is square is a constant, so we can call it as a W naught, and this 2 L upon twice R can be written as tau, which can be being like a time constant. Now we can think of that this heat dissipated is equal to W naught and this number. Now if we need to find the total amount of heat dissipated, then means we need to put this final time as infinity. So the expression will turn out as W naught. So W naught is going to be the total amount of heat dissipated, and this is what we need to find out. So we are working like there are two unknowns. One is W naught, another is this tau, and some information has been provided to us. So it says delta W1 is the heat dissipated in 0.1 seconds. So we'll put T as 0.1 and W as delta W1. So delta W1 will become W naught within bracket 1 minus e raised to power minus 0.1 by tau. Now let's consider this e raised to power minus 0.1 by tau as another variable that is x, or another expression or symbol as x. So this is x, where x is a given quantity that's going to be like dependent on tau and this expression. So it's will simplify to W naught within bracket 1 minus x. Then next time is 0.1 seconds. So overall we can take time 0.2 seconds, and the amount of heat will be delta W1 plus delta W2. So delta W1 plus delta W will be equal to W naught within bracket 1 minus e raised to power minus total time, which is 0.2 second divided by tau. So this will be like W naught 1 minus, and this is written as a square of this, right? So that could be written as x square. Now using these two, we can relate this x. So what I have done, I have divided these two expressions. So delta W1 divided by delta W1 plus delta W2 is equal to, from here W naught will get cancelled out. It will be like 1 minus x, and it could be written as 1 minus x, 1 plus x. So 1 minus x is also getting cancelled out. So it will be like 1 upon 1 plus x. Now we can have this cross multiplication and find this x value. or we can simply write 1 plus x turn out to be delta W1 plus delta W2 divided by delta W1. Now we know from this expression, the very first expression, we can write 1 minus x as delta W1 divided by W naught. Now these two expressions if we add, basically we are trying to eliminate this term. So you'll find that this x will get cancelled out and we will find 2 over here. And this will be like delta W1 plus delta W2 divided by delta W1 plus this term which is delta W1 by W naught. Now we can bring this term this side, so it will be like delta W1 by W naught is equal to, when it turns this term comes this side, so it will be like 2W1 minus W1 minus delta W2, right? So it will be like delta W1 minus delta W2 divided by delta W1. We are looking for this W naught, which was our final response, right? So W naught will be equal to, we can have a cross multiplication, so that will be like delta W1 square divided by delta W1 minus delta W2. So the total amount of heat dissipated is going to be dependent on these given heat dissipations as delta W1 square divided by delta W1 minus delta W2. Now these numbers are known to us. Delta W1 is 0.01 joule and delta W8 is 0.006 joule respectively, right? So we can use these numbers and simplify this numerical value and settle down to this number which is 0.025 joule. So that's our final response, and this is expression for the final response. So that's how we are able to solve this problem. Thank you.